This video is for Math 1332 on Monday, August 7th, as we start our fourth of 5 weeks of the semester. And we're going to be covering sections 11.3 and 11.4 today. Okay. 11.3 is combinations, 11.4 is probability. Combinations are very much related to permutations in that it's exactly the same except order doesn't matter. So there's really three main what I call counting principles, which is how many ways can you do something. And in fact, this is what they're doing right here, is trying to have you decide which kind of problem you have now that you're learning more of them. So it was a little easier last week because we just had our two basic types and they were different from each other, but now this one is very similar to the section 11.2. So if you're going to make a series of decisions, two or more decisions, and you need to pick one of these, one of these, one of these over and over again, that's the fundamental counting principle. That's the easiest kind, and you just multiply all the possibilities together, like the Olive Garden example. In the other two, permutations and combinations, you're not doing one of these and one of those, you're doing so many out of a total. Like here it says there's 48 people that are going to be given an experimental drug, and 104 people have volunteered. How many ways can you select these 48 people? So I'm trying to choose 48 out of 104 people. So as soon as it's 48 out of 104, then it's definitely not the fundamental counting principle. We're not going to do one of 104 and one of 48. So this is either a permutation or a combination. Anytime you're selecting 48 out of 104, it's definitely one or the other. And they're very, very similar except for whether order matters or not. Now, sometimes it's hard to tell if order matters or not. So another way to tell is, are you treating these people differently or not? Or whatever they are, the objects of the people. Are they being treated differently or are they being treated similarly? Well, this is a medical research of an experimental drug, not multiple drugs. If we were doing something like, what's better, aspirin A or aspirin B or aspirin C, and we had different medicines, then we'd be treating the subjects differently, because people would be getting different medicines. But if you're just going to test one drug and see is this effective or not, then all the people that get selected are going to take the same drug. So that means you're treating them all the same. And if you're treating them the same, it's a combination, not a permutation, because the order doesn't matter. The order of the patients selected doesn't matter, because all 48 are eventually going to get the same medicine. So that's a good example of a combination. Does the following problem involve a permutation or a combination? Okay, 47 people purchase raffle tickets. 3 winning tickets are selected at random. The first prize is $1,000, the second prize is $500, and the third prize is $100. How many different ways can the prizes be awarded? So I've got 47 people that bought tickets, and I need to choose 3 of them to win prizes. I got to choose 3 out of the 47 people. So this is definitely a permutation or a combination and not the fundamental counting principle. I'm not doing 1 of 47 and 1 of 3. So I'm doing 3 out of 47, but the 3 people that get picked, one person gets $1,000, the second one only gets $500, the third one only gets $100. I'm going to be treating the winners differently. The person who gets the first ticket drawn is probably going to take the best prize, the $1,000 winner. And whoever goes third, they win something, but it's not as good as the first person. So this is a perfect example of a permutation, because the order did matter here. It does matter. I would rather be first than second or third, because I'm treating the 3 people differently. They're not all getting the exact same thing, like the same medicine. They're getting 3 different prizes. Now you could repeat this number 2, and if the prizes were $500, $500, $500, then it would switch to a combination, because then you're treating all the people the same. So that combinations and permutations are so close, that's literally all it comes down to, is whether you're treating them differently or the same. which tells you whether the order matters or not. Okay, now we want to calculate a combination. We did these with permutations last week in the last video. This one says 9 combination 5. So just like the permutations we did last time, you always put the bigger number first, and then you write down whether you think it's a combination or a permutation by putting a C or a P, and then you put the smaller number last. So even if they word it backwards, if they say 5 out of 9 people are selected, or out of 9 people I need to pick 5, either way I'm going to do this. Now there is a formula for this. It's very much like the permutation formula. You do the front number factorial in the top, just like in a permutation. And then in the bottom, you do subtract both of these in a factorial, just like a permutation. So even when you're calculating a combination, it's very similar to calculating a permutation. All of this is how you would do a permutation. If you do that much, that's a permutation. A combination has one extra thing. The back number 5 also gets a factorial in the denominator. And if you do this 9 minus 5 and make that a 4, then the 2 numbers in the bottom will always add up to the top. And you may remember in permutations that there was a shortcut to doing this too. I'll show you that in a second here. But if you were calculating this out, the 9 factorial would be 9 times 8 all the way down to 1. But just like with permutations, some of it's going to cancel out with the bottom. So I'm not going to write this out all the time, all the way down, but I just want to do it once so you see what happens. There's 9 factorial. And then there's this front 5 factorial. And then, whoops, that's supposed to be a 1. And then there's a 4 factorial. Well, before, this 5 factorial wasn't here. When we did permutations last week, we wrote 9 all the way down to 1, and then there was this 9 minus 5 that we would subtract a 4, then do 4 all the way down to 1. And this 4 all the way down to 1 would always cancel with stuff in the top. And remember, in a permutation, the shortcut is you start at the front number 9, and you decrease by 1 however many times this number is. So by starting at 9, 8, 7, 6, 5, stopping there, you're stopping there because that's 5 different numbers. That's a permutation. What's different in a combination is the extra 5 factorial in the bottom. And there's always an equal amount of numbers too. Notice that there's 5 numbers in both the top and the bottom. So that's what's different, is if you calculate the permutation first, then you also have to divide by that other factorial in the bottom. Now you can still cancel stuff. I could have this 5 cancel that 5. And 3 times 2 equals 6. And 4 can go into 8 twice. So all that's left is 9 times 2 times 7. 9 times 2 times 7 is 126. And the shortcut, what I like to do instead of doing all this, is 9 combination or permutation 5. I start with 9. I start decreasing by 1 until I have 5 numbers. 1, 2, 3, 4, 5. And then if it's a permutation, that's all you do. Just take out your calculator and type it in. If it's a combination, then you include the back number factorial in the bottom, because the rest of it canceled out. And even if you don't like this shortcut, you're going to eventually get to it anyway, because if you do it all the way out, the 4s are going to cancel all the way down, and that's my shortcut right there. But I do that even with permutations. So 126 is the answer to number 3. Okay, 8 combination 1. Well, first of all, let me just tell you this. 8 combination 1 or 8 permutation 1. We learned a couple of shortcuts for permutations if it ended with a 0 or if it had the same number as the front. Another thing that's true is whether it's a permutation or a combination, if the back number is a 1, the answer is whatever the front number is. And really what's happening is, whether you do it with a permutation or a combination, 8 permutation 1, using my shortcut, you would write the first number 8, and you would decrease by 1 until you have one number. Well, I already have one number, so that's literally the answer right there. And then in a combination, what would happen is you would do that first. But then what's different about a combination is then you also divide by this factorial. 1 factorial is 1, and you still get 8 that way too. Or if you did the formula all the way out for a permutation, it would be 8 factorial over 8 minus 1 factorial. And that's 7 factorial. 8 minus 1 is 7. So if you wrote 8, 7, 6, 5, 4, 3, 2, 1 in the bottom, and then in the top, and then the bottom was 7, 6, 5, 4, 3, 2, 1. The 7 all the way down to 1 would cancel in both the top and the bottom, and all that would be left is an 8. And the only thing different in the combination formula is you would have that first, but then you would also have this 1 factorial. But 1 factorial is 1, and anything times or divided by 1 is itself, so really a 1 factorial when there's other things in a problem doesn't matter. In fact, remember those problems about Mississippi where I was just crossing out the 1 factorials? So a 1 factorial, unless that's the entire answer, it's not going to affect any other answers. But this is another possible shortcut. You could just know that if I'm doing a permutation or a combination and the last number is a 1, the answer is just automatically whatever the front number is. If both numbers are the same, then in a permutation, you get that number factorial. If this was 11 permutation 11, the answer would be 11 factorial, and you'd have to do 11 times 10 times 9 all the way down to 1. If it's a combination, the answer is just automatically 1, because what's going to happen, whoops. There we go, something clicked there. Okay, so see, the answer is automatically 1, because what's really happening is you're taking the front 11 and doing that as a factorial in the top. And then you subtract the two numbers as a factorial in the bottom. This is a permutation so far. And 11 minus 11 is 0. Remember that 0 factorial by rule is 1. So if you just do this much, you have a permutation, and you literally have 11 factorial divided by 1, which is 11 factorial. But in a combination, there's the back number 11. That also gets a factorial in the bottom. And the 0 factorial doesn't matter if there's other stuff here. So I literally get 11 factorial divided by 11 factorial in a combination when both numbers are the same, and anything divided by itself is 1. So that's another reason why this answer is just automatically 1. Okay, 20 combination 4. They just want me to calculate this. You got two choices. Here's the method I like better. 20 combination 4. The shortcut method is you start at 20. You decrease by 1 until you have this many numbers, until I have 4 numbers. So 1, 2, 3, 4. Stop. If it's a permutation, that's all you do. If I would have had 20 permutation 4, I would just multiply these out on a calculator. The combination, what's different is then you also divide by this down to 1. And you'll always have an equal amount of numbers in the top and the bottom. There shouldn't be 4 numbers in the top and 5 numbers in the bottom, for example. So then I could say, okay, 4 can go into 20 5 times, or you could pick it a different, sometimes you can have more than one choice to go to. 3 can go into 18 6 times. And 2 can go into 6 3 times. You can use the same number more than once. And the 1 doesn't matter now that there's other stuff here. So you can often cancel the entire denominator before calculated. All I have left is 5 times 19 times 3 times 17. 5 times 19 times 3 times 17. 4,845. 4845. 4845. And if you wanted to do the formula, it would have been 20 factorial for the front number over 20 minus 4 factorial, just like in a permutation. But then there would also be a 4 factorial if you have a combination in the bottom. But 20 minus 4 is 16. 16 factorial is 16, 15, 14, all the way down to 1. And it would cancel most of the 20 factorial that goes from 20 down to 1. It would cancel the 16 down to 1 on both of them. So all that would be left is literally this right here. The top would just be 20, 19, 18, 17 because the 16 down to 1 would cancel. And the bottom would just be this 4 factorial, 4, 3, 2, 1, and then the calculator will be the same. So in essence, my shortcut happens even if you're doing the formula anyway. 18 combinations, 0. If you get anything permutation or combination 0, the answer is automatically 1. Think of it this way. Say I have 18 prizes to give away, and if they're all different, then it's a permutation. If they're all the same, it's a combination. So normally that matters. But whether I have the same or different prizes, if I have 18 prizes to give away, and I'm going to give them away to nobody, how many ways can I give no prizes away? There's one way to do that. I keep all the prizes myself. So if it's, I maybe should make a list here. If you get any number permutation 0 or any number combination 0, both of these equal 1. There's only one way to do that. If you get any number permutation 1, I should put an or here, or any number combination 1, the answer is whatever the front number is, the n. If you get n permutation n, where both numbers are the same, the answer is the same as whatever n factorial calculates to. Or if you get n combination n, then the answer is 1. If I have 18 identical prizes and I'm going to give away to 18 people, there's one way to do that. Everybody gets a prize. And it doesn't matter what the order is because all the prizes are identical, so you just come up and get your prize and we're all done. If I have 18 different prizes, then order matters, and I can't just have everybody come up and grab a prize. I need to figure the order out first, and actually it'd be a lot of ways to do that. So the good news is if the back number is a 0 or the back number is a 1, then it doesn't matter if you have a permutation or a combination, the answer is automatic. If you have the same number in the front and the back of a permutation or a combination, then they have different answers actually. But they both have like shortcut answers. Okay, you can also do permutations or combinations in some calculations, like this is an example of a division problem. What if I have 12 combination 7 divided by 6 combination 5? You just basically calculate both of these separately and then divide the answers at the end. So I'm going to get two answers like I've gotten on previous problems. Each half of this is like previous problems. 12 combination 7, you would do 12. Here's my shortcut way. 12, 11, 10. Keep going until you have 7 numbers. So 4, 5, 6, 7 numbers right there. And then the bottom is the back number 7 all the way down to 1. 7, 6, 5, 4, should be an even amount of numbers too, in the top and the bottom, 3, 2, and 1. They both have 7 numbers. And you can often cancel the entire denominator out. The 7 and the 6 just cancel out directly. 4 times 2 could be 8, although I could have had the 4 go into 12 if I'd rather do that. It doesn't really matter. 3 can go into 9 3 times. And 5 can go into 10 twice. And the 1 doesn't matter. So all that's left is 12 times 11 times 2 times 3. 12 times 11 times 2 times 3. The top is 792. And this would normally be an answer. Normally that would have been an answer to the last handful of problems. You normally just do this once, but they're just making up a problem here where what if you have 2 of them divided? 6 combination 5. Okay, start over again. Start with 6. Decrease by 1 until you have 5 numbers. 1, 2, 3, 4, 5. And then if you're doing a combination, then you also have the 5 down to 1. And of course the 1 doesn't matter, but notice that 5, 4, 3, 2 cancels 5, 4, 3, 2. The answer is 6, literally. So then the final answer is whatever 792 divided by 6 is. 132. So you're basically doing problems like the last handful twice and then dividing the answers. 132. Okay, now they're just throwing everything you've learned so far at you at once. Here's a 9 permutation 3 divided by a 3 factorial and then minus a 9 combination 3. Just completely arbitrary calculation. This is anything special, but 9 permutation 3 divided by 3 factorial and minus 9 combination 3. Well, 3 factorial is clearly 3 times 2 times 1. That's 6. 9 permutation 3, all you would do is 9 times 8 times 7 and stop after 3 numbers. And in a permutation, there's nothing to divide by. So that's just 9 times 8 times 7. The top is 504. And now I could divide by this 6 right here. So the fraction part is 84. Minus, and now I got to calculate 9 combination 3. Well, that would start off like 9 permutation 3. That would be 9 times 8 times 7. Stop after 3 numbers. But then with the 3 in the back, then you also divide by 321. Which coincidentally was what we did right here. So it's going to turn out this is going to have the same answer by coincidence. If they would have given me different numbers here, like maybe this was 9 permutation 3, if this had been like 10 combination 5, then this wouldn't have happened. But just because the way a combination is calculated, it has that extra 3 factorial in the bottom. So by putting a 3 factorial in the bottom here, it made these answers the same. So that's 0. Anything minus itself is 0. Okay, now they got 3 combinations, 2 of them multiplied together and 1 divided. There's an 8 combination 2. This is number 10. 8 combination 2 times 9 combination 1. And there's a shortcut for that one. If it ends with a 0, a 1, or the same as the front number, there's a shortcut for it. And then it's divided by 27 combination 3. Anything combination 1, the answer is whatever the front number is. So this is just 9, literally. It's actually 9 factorial divided by 9 minus 1 factorial and an extra 1 factorial, but The 9 minus 1 factorial is 8 factorial, and that cancels all but the 9 in the top. And then the 1 factorial equals 1, so it doesn't matter. So that's just 9. 8 combination 2, you would do 8 and 7, stop after 2 numbers. And then you'd also divide by 2 and 1. And you could either say 56 divided by 2, or you could have 2 divide into 8 4 times. 4 times 7 is 28. So the top is 28 times 9, 252. For the bottom, I'd have to do 27, 26, 25, stop after 3 numbers, and then divide by 3, 2, and 1. And again, you could do 27 times 26 times 25, write it down, and then 3, 2, 1 is 6, and divide the 2. But I always like to reduce first because it just makes numbers smaller. 3 goes into 27 9 times. 2 can go into 26 13 times. Oops. So the bottom's all gone. The top's just 9, 13, and 25. 9 times 13 times 25. 29, 25 is the denominator. Now, there's a part of the next section, 10.4, I'm sorry, section 11.4. It's called probability. This happens in probability sometimes, where you have these 3 combinations and you divide them. But one thing you're about to learn in the next section is probability always has an answer between 0 and 1. It's never an integer. Like all the answers we've had so far have been integers. But in a second, we're going to get problems where none of the answers will be integers, and they're all going to be decimals or fractions. So that's why this is the first time in this chapter you've seen an answer that wasn't just an integer. And then I got to see how far do they want it rounded. Type an integer, or they want an integer or a fraction. Okay, well, later they'll take decimals too, but that's why I had to read what they wanted. Okay, so the only issue is, does 252 over 2925, does that even reduce? Because it's hard to tell. Well, it's not an integer for sure. I don't know if it's if it's a reducible fraction or not. 252 divided by 2925, we'll find out here right now if it reduces. Apparently it reduces. See how it says, although your answer is equal to the correct answer, it's not in the correct form? Okay, so that's hard to know what these divide by. But 252, since it ends with a 2, it's definitely an even number and divides by 2, but this ends with a 5 and doesn't divide by 2. The top won't divide by 5 because it ends with a 2. Okay, so 252 divide by, maybe they divide by 3. Let's try the check for 3. For 3, you add all the digits together. 2 plus 5 is 7, plus 2 is 9. Since 9 divides by 3, then 252 divides by 3. And the bottom is 2 plus 9 is 11, plus 2 is 13, plus 5 is 18. That divides by 3. So this will at least divide by 3. It might even divide by 9. In fact, it does divide by 9 because if they're divisible by 9, they divide by 9 too. So you could either divide by 3 or 9. I'm going to jump right to 9 and get 28. I actually ended up dividing by 9 instead of 3. But if you did 3, you could do 3 again after you got the first reduced. And then you would have what I have, 325. Now 28 only divides by 2, 4, and 7. And neither 2 nor 4 is going to divide into 325 because it has to divide into an even number only. I don't know if 7 divides into this, so let's try divide by 7. No. So I'm thinking this is as far as it's going to reduce. 28 over 325. And this is only because they said type an integer or a simplified fraction. They're kind of forcing me to do this here. Whoops. Can't get it to the spot where I want it there. 28 over 325. But I did have an equivalent answer. The two, I guess I don't have it here anymore, but if you did 28 divided by 325, this decimal is the same thing I had. Well, it is down here, see? So it is the same, 068, 068. So if they would have let me do a decimal, this would have been a lot easier, but it got messy because it was reducing such a large fraction. Okay, now you get these word-like problems where you have to decide what kind of problem you have and then also calculate it. This is going to sound very much like the previous section too. An election ballot asks voters to select 4 city commissioners from a group of 13. How many ways can this be done? So we're not picking 1 out of 4 and 1 out of 13. We're picking 4 out of 13. We're picking 4 out of 13, so this is either a permutation or a combination. Does order matter or not? Am I treating these people differently or not? Well, in these kind of things where you have voting going on, if you have a president and a vice president and a secretary, I think we had that in the last section. That's a permutation because those jobs are different. It's different to be a president than it is to be a secretary. Try telling Donald Trump he has to be the secretary today, he would throw a fit, and no, I'm the president, I have to be the most important person. But this is not that case. It doesn't say we have a president, a vice president, a secretary. We have 4 city commissioners. This is the other thing they do. They have like a panel of people who all have an equal vote. So that way you don't have one person trying to dominate everything. So an election ballot asks to vote for 4 city commissioners. City commissioners all have the same job. So I'm picking 4 out of 13. That's how I know it's either a permutation or a combination. And then because it doesn't specify that the jobs are different, it just says they're city commissioners, that makes it a combination. And then you always put the bigger number first, combination, and then the smaller number. If it said they were going to be president and vice president and secretary, then I would have 13 permutation 4 potentially. In fact, one of the problems in the last section was like that. If it was a permutation, you would just do 13 times 12 times 11 times 10 and stop right there. That would be the permutation answer. 13 times 12 times 11 times 10. There would be nothing to divide by. If it's a combination, then you also divide by the back number 4 all the way down to 1. 4 factorial. The rest cancels out. The 1 doesn't matter either. 2 can go into 10 5 times. 3 can go into 12, or I could say 4 times 3 is 12 and just get rid of all 3 of those at the same time. So there's a 13, there's an 11, and there's a 5. That's all that's left. And we're back to getting integers too. 13 times 11 times 5. 715 ways to do that. Of 10 possible books, you plan to take 7 with you on vacation. How many different collections of the 7 books can you take? So this is very vague right here, and you might confuse it with the other problem if this was just randomly placed on a test somewhere. Because are you treating these books differently or not? Does the order that you read the books matter or not? That could be debatable, actually. Because say you're on a vacation and you want to read some books, maybe you're enjoying your vacation so much you end up not reading all the books. And then whatever one you read first had an advantage of getting read, and the one that you were going to read last, you never even got to it. But you should never, the way the homework works is you should never try to read into a problem like that and assume something's going on that's not specifically stated. So not only does this say it's a combination, because we're in the combination section, but they consider this a combination because it's not about when are you reading the books. To them, it's about are the books going with you or not. You either throw them in your suitcase or your travel bag or you don't. So 7 of the books get thrown in your suitcase and the others stay home. And as long as you're in the suitcase, you get to go on the trip, and whether you get read or not apparently doesn't matter here. So I'm choosing 7 out of 10 books to go on a vacation, and Apparently we don't care if you read them or not, but you're doing 7 of 10, and we're in essence treating all the books the same by taking them on vacation with us. So this will become a 10 combination 7. And that means the top, you start at 10, decrease by 1 until you have 7 numbers. 1, 2, 3, 4, 5, 6, 7. And then since it's a combination, then I also have to divide by 7 all the way down to 1. 7, 6, 5, 4, 3, 2, 1. And the 7, 6, 5, 4, that's in both of them. I can definitely get rid of all that. And then 3 can go into 9 3 times. 2 can go into 8 or 10, your choice. I'll do it into 8, just because I like leaving 10s in the calculation. So 10 times 3 times 4, that's easy even without a calculator, because 3 times 4 is 12, and then 12 times 10, you just put a 0 on the end of it, 120. To win the lotto in one state, one must correctly select 7 numbers from a collection of 48. I got to pick 7 out of 48 numbers. The order in which the selection is made does not matter. Here they made it very clear that order does not matter. And maybe if you know anything about the lottery, that is the case in the lottery. The lottery is hard enough to win as it is. Imagine if you had to get the numbers exactly in the same order. They draw them out of the barrel. So then nobody would ever win. So yeah, that's the one good thing is when you get a lottery ticket, you can tell them the numbers in a mixed up order if you want. And then when the computer prints out your ticket, it rearranges the numbers from lowest to highest so you can search for the winners more easily. So because the order doesn't matter. So 48 combination 7 for a particular lottery, you would start at 48, decrease by 1 until you have 7 numbers. So 1, 2, 3, 4, 5, 6, 7. And then the bottom would be 7 down to 1. And there's not going to be anything that cancels instantly like I had on the last problem, because none of the numbers in the bottom are also in the top. But we don't need the 1. Now I can just go slowly in whatever order. You want to start with the 7 or the 2, doesn't really matter. 7 times 6 is 42. That helped a little. 5 can go into 45 9 times. 4 can go into either 48 or 44, your choice. I'll do the 44 11 times. 3 divides into any number that adds up to a multiple of 3, 7, 10, 11, 12. It can go into 48 16 times. And then I can have the 2 go into either the 46 or the 16. I could do the 16 again if I want. But I'll just do it in the 46 to make that a smaller number 2, make that 23. So I cancel the entire bottom out. And then there's so many numbers in the top, I'm going to pull this down so I can see it at the same time. All that's left is 16 times 47 times 23 times 9 times 11 times 43. So there would be almost 74 million ways to play that lottery, and that's why people don't win very often. If you buy one ticket, you have a 1 in 73.6 million chance of winning. 73 million. $629,072. Now say you were Elon Musk and you had $73 million in your back pocket. In theory, you could buy one of every ticket and be sure of winning. If the prize was $1 billion, maybe that would be worth it, but it might be kind of hard to stand at the gas station and read 73 million different possibilities, if you could even write them all down. Okay, how many ways can a committee of 2 Democrats and 3 Republicans be formed from a group of 12 Democrats and 11 Republicans? You remember those problems where we had more than one of these to do at a time? Like this. That's where these came from, actually. So you basically have a combination for the Democrats, you have a combination for the Republicans, because these are just committees. There's no president, vice president, or secretary. So we're just going to have a committee. Committees are always combinations because everybody gets an equal vote. So I'm going to pick 2 Democrats out of 12 Democrats. Just do the Democrats first. 2 Democrats out of 12 Democrats. That's 12 combination 2, which would be 12 times 11. Stop after 2 numbers and divide by 2 and 1. And 2 can go into 12 6 times. The 1 doesn't matter. 11 times 6 is 66. So you want 2 out of 12 Democrats, and then you want 3 out of 11 Republicans. And remember, always put the bigger number first. 3 out of 11. So this would be 11 times 10 times 9, and then you would divide by 3, 2, 1. The 1 doesn't matter anymore. 2 can go into 10 5 times. 3 can go into 9 3 times. So it's 11 times 5 times 3. 11 times 5 times 3 is 165. There's 66 ways to pick the Democrats. There's 165 ways to get the Republicans. And we want both of these. So this is and this many Democrats and this many Republicans. And is typically when you multiply in this chapter. So I just need to multiply by 66. 10,890. $10,890. Okay, final question in this section. In a race in which 5 automobiles are entered and there's no ties, how many ways can the first 3 finishers come in? We had a similar one like this last section, and the reason they threw this one here is they don't want you to just automatically assume you have a combination. You've learned permutations already. Race order matters. Everybody wants to be first. If you don't finish first, people don't care about you. Now, sometimes first 3 finishers, okay, there could be prizes for all 3. Maybe there's a gold medal, a silver medal, or bronze medal. But even then, the gold is better than the silver, and the silver is better than the bronze. So in a race with 5 automobiles, 3, how many ways can the first 3 come in? They're just throwing a permutation here to see if you remember that from last section. This is 5 permutation 3, because order matters in a race. And then if you're calculating this, you just do 5, 4, 3, stop after 3 numbers. There's nothing to divide by when you're doing a permutation. So 5 times 4 times 3 is 60. That was just a quick review right there of what we did in section 11 too. In fact, there was a problem in there about a race there too. So that's section 11.3. Got 100% on that now. Save this. 11.4 are basics of probability. And some of these counting techniques that we learned, the fundamental counting principle, permutations, combinations, these sometimes help when you're doing probability, which is why they're teaching those ahead of time. Fundamentals of probability. Probability is how many good things can happen to you divided by how many total things there are. So you're probably familiar with 6-sided die, but they do make special dice that have more than or less than 6 sides for certain games. So there can be an 8-sided die. An 8-sided die has 8 equal sides that all have a 1/8 chance of coming up. And they listed all 8 of them there, 1, 2, 3, 4, 5, 6, 7, 8. So anytime you roll it, one of those 8 things is going to happen. When you list all the possible ways your experiment can happen, this right here, that's called a sample space. And not only is it good to know what you're dealing with, but it can instantly give you your total. There's definitely 8 numbers right here. That's my total. So without even reading what they want me to find the probability of, I'm going to put a fraction, because notice it says type in an integer or a simplified fraction. So they don't want decimals here. But the denominator has to be 8 no matter what. I always like to get the total first, and then I never have to worry about it, especially because some problems will have like a part A, part B, part C, and then you're just putting over 8, over 8, over 8 every single time. So the total is always the bottom, 8, and then the top is going to be less than or equal to 8. It can be 8, and it can go all the way down to 0, or anything in between. It's going to be a 0 through 8. So like, what if they said, roll the die and try to roll a 12? Well, I can't roll a 12 if I only roll it once. So there's 0 ways that's good for me. The answer would be 0 over 8 if that was the question. Or if they said, roll a number less than or equal to 8, I'm always going to do that. So then the top would be 8 over 8, which is 1. So all probabilities between 0 and 1, no matter what. It can be 0 and it can be 1, but usually it's in between. They want me to find the probability of rolling an even number on this 8-sided die. Well, 4 of these numbers are evens. 2, 4, 6, and 8. 4 out of the 8 are even numbers. That's very typical for probability, where you do how many good cases? 4 over the total 8. Now it does say a simplified fraction, so if you can reduce it, they're going to force you to. 4 divided by 8, both of those can divide by 4, so 4 divided by 4 is 1. And 8 divided by 4 is 2, so they're forcing me to reduce it to 1/2. But it would have been equivalent to 4 over 8. Okay, now we have a 12-sided die. And there's 1 through 12 that can come up. So instantly, I can put a 12 in the bottom before any possible reducing. And it's going to be 0 over 12 all the way up to 12 over 12. I have to have some answer in that range. Now I'm going to read what they want. They say, find the probability of rolling a number greater than 1. Well, all the numbers are greater than 1 except for 1 itself. So 11 of the 12 numbers are greater than 1. That's how many good cases there are. So don't just put 11. I get that a lot. The answer is not 11. In fact, it's impossible to be 11. Probability can't be bigger than 1. So the final answer can never be bigger than 1. If you put 11, it's an impossible answer. So that's why I always like to get the total out of the way so you don't forget to do that, because I get that all the time, especially in my statistics classes that I teach. So 11 out of 12, and that doesn't even reduce because 11 is a prime number. So if these, the only way, see how it says type an integer or a simplified fraction, the only integers are 0 and 1. Everything else is going to be a fraction. And when they're fractions, the top can never be bigger than the bottom, actually. You can't get more successes than the number of times you do it. I saw a bumper sticker, and it said 5 out of every 4 people have trouble with fractions, including the person who came up with that quote. Because if you only ask 4 people, do you have trouble with fractions? How can 5 say yes if you only ask 4 of them? But I get people that do that on tests. They'll put the probability is 5 over 4, and it's like, that's an impossible probability. You can't get the top to be bigger than the bottom. Okay, also while I'm thinking about it, let's do our magic word of the day. We're going to go on a little bit of a tour around the country this week. So the magic word today is Dallas. Send me an email for Monday, August 7th, and put the magic word is Dallas. Okay, so now we're rolling a 4-sided die. The bottom can, at most, or the bottom is a 4 if it's going to stay a fraction. Whoops. The bottom is 4. The top has to be 0, 1, 2, 3, or 4. It can be as low as 0, it can be as high as 4, or anything in between. It can't be bigger than 4. 5 out of 4 is impossible. Find the probability of rolling a number less than 13. All 4 of these numbers are less than 13. So this is the highest you can ever get, 4 out of 4. And since that divides, then we need to divide it. 4 divided by 4 is 1. So that's when you get an integer answer. If they would have said, find the probability of rolling greater than 13, then the answer would have been 0 out of 4, which is 0, because you can't get, none of these numbers are greater than 13. You wouldn't be able to get any of them. 12-sided die, okay. And that means the bottom can only be a 12 if it's going to stay a fraction. Find the probability of a number greater than 19. I just said that. So greater than 19, none of these numbers are greater than 19. There's literally 0 good cases for me. None of these numbers are good for me. I can't get any to be greater than 19. So I have a 0 out of 12 chance of this happening. And 0 divided by anything is 0. So they'll count it wrong if you don't reduce it to 0. But 0 is that's the other way you can get an integer answer. So in this entire section, if you get 0 or 1, they're integers. Everything else is going to be a fraction no matter what. Okay, a fair coin is tossed 2 times in succession. There's 4 possible things that can happen. You can get heads and heads, that's 1. Or heads first and tails second, that's 2. Or tails first, heads second, that's 3. Or they could both be tails. There's 4 possible things here, and they were nice enough to list all 4 of them for you. If you take statistics, Math 1342, they make you write the sample space down, actually. But here they wrote it down for you. Now you know your total's 4. The good cases have to be 0, 1, 2, 3, or 4. How many of these 4 things that are listed in the sample space, how many of them have what it says right here, exactly 1 head? Because it could be 1 or more heads, or 1 or less heads. But this is exactly 1. This heads tails has exactly 1, and the tails heads has exactly 1. So it's 2 out of 4. 2 good cases out of 4 total, and that reduces to 1 out of 2. And because it says simplified fraction, you have to reduce it or they'll count it wrong. Okay, same question. We got heads, 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 tails, tails, heads, tails, tails. There's 4 possibilities here. That's my total. Oh, this is the same question. Find the probability of exactly 1 head. That's weird. So 2 out of 4. 1 out of 2. I don't know why that came up exactly the same. In fact, let me go back and try another and see if that was just the luck of the draw here. Similar question. Okay, yeah, I think that was just the luck of the draw that one came out the same. But now notice I have 3 coins going on. So now it turns out there's 8 possible things in the sample space. There's 8 ways 3 coins could come up. So I look at the sample space, I count how many there's there. There's 8 of them down there. There's 8 total things that can happen when you flip 3 coins. How many of these have exactly 0 tails? Only this first one does. The one with all heads. So only 1 out of 8 has no tails in it. All the rest have 1 or 2 or 3 tails. So 1 out of 8. So I just redid question 6 just because for some reason my questions 4 and 5 came up the same at first, but when I tried another version of 6, I got a completely different type of problem. Okay, this might seem the same as the previous 2 before I tried another on number 6. There's 4 possible ways 2 coins can come up. If you do 2 coins, it's always over 4. If you do 3 coins, it's over 8. If you were to do 4 coins, it would be over 16. Now, the 2 problems I got that were the same, it said find the probability of exactly 1 head. Now, it doesn't say exactly 1. It says at least 1. At least 1 means 1 or more. And that could mean 2 heads in this case. So it includes the 2 heads. It includes both of the ones that have 1 head. So this is 3 out of 4, not 2 out of 4. There's 3 good ones now out of 4 total. And 3 out of 4 doesn't reduce, so that's it. Okay, it turns out it doesn't matter if you're doing heads and tails on a coin, or evens and odds on a dice, or boys and girls in a family. So here's a case where the family has 4 children, and I just said, remember, if there's 2 coins, you get 4 in the bottom. 3 coins, you get 8. If you do 4 coins, you get 16, but you don't even need to remember it because they list it out for you. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 families, possible families in the sample space here. So if you flip 4 coins, or if you have 4 children, there are 16 different ways you can have boys and girls. And in birth, we'll assume there's no twins here. So there's 4 children born separately at separate times. So some are older than the others. And then people care about, okay, what happened first, the boy or the girl? Which one happened last, boy or girl? So birth order is important here. How many of these 16 families have exactly 3 boys, 3 male children? Exactly 3, not at least 3 or at most 3 or greater than 3 or less than 3. They could ask that too. But this one says exactly 3. So I need to just check each one. How many of these have 3 M's with them? So far, none of them do. I went through the first 7. There were no 3 M's. Here's still 2 M's, 2 M's, 2 M's, 2 M's. Here's one. If the female is first and then you get 3 straight boys, that's 1. Or maybe the female second and the other 3 are boys, there's 2. Or the female could be third and the other 3 can be boys, that's 3. Or maybe the female's the youngest child and the first 3 were all boys, that's 4. There's 4 out of 16 that have exactly 3 boys. One has all 4 boys, one has all 4 girls, but only 4 have exactly 3 boys. And 4 out of 16, both of those divide by 4, so 4 divided by 4 is 1, and 16 divided by 4 is 4, so there's a 1/4 chance of that. Here's a family with 3 kids, so now there's only 8 possibilities. Just like if I flipped a coin 3 times, there'd be 8 possibilities. So 3 kids or 3 coins, it's going to be over 8, unless it reduces or comes out to an integer. So now they want how many have at least 2 female children, at least 2 girls. I always associate at least with driving cars because students get at least and at most mixed up a lot. Think of at least 16 to drive a car. You have to be at least 16 to drive a car. Say that to yourself a bunch of times. And then you can know, yeah, at least that's the one where it's that number and up, because we know drivers are 16 and up. We don't have any babies driving. So at least 2 means 2 and up. And this is a family of 3 kids, so that means 2 or 3 girls in a family. How many of these have 2 or 3 girls? Because it really means 2 and higher, but the most I can have is 3 girls in a family of 3. So the first one has no girls, then there's 1 girl 2 times. Then there's a 2-girl one right here. Then there's another one with 1 girl, 2 girls, 2 girls, and 3 girls. So there's 1, 2, 3, 4 of these. 4 out of 8 have 2 or 3 girls. And 4 divided by 8 reduces to 1 divided by 2. So you got a 50% chance to get at least 2 females, and also a 50% chance to get at least 2 boys too, which should make sense because boys and girls happen roughly equally. Okay, 2-sided die. You can use this chart right here. It's just a little long to deal with. It turns out there's 36 possible ways to roll 2 dice and sum their results together. Many board games like Monopoly or casino games like craps involve rolling 2 dice and adding their results together. And it even says there's 36 equally likely outcomes here. So as soon as they say that, or as soon as you realize 2 dice always have 36 for the total. So I always like to put that down right away, 36. So find the probability that you get 2 numbers whose sum is 12. So this is where this could take a while in theory, because you might have to add these, searching for the ones you're looking for. Like this first parenthesis right here, 1 plus 1 is 2. The next one's 1 plus 2, that's 3. 1 plus 3 is 4. 1 plus 4 is 5. I got to find any of them that add up to 12. Well, it turns out only 6 plus 6 equals 12. There's no other way to get a 12 with 2 dice. So there's a 1 out of 36 chance of getting a 12. If you play Monopoly, if you play craps, see, in the casino game craps, you can bet that somebody's going to roll a 12, but it only happens on average 1 out of every 36 times the game is played. And if it costs $1 to play the game, if you get what you're trying to get, if they roll what you're trying to bet on, and you're betting on a 12 coming up, if it was a fair game, they should pay you $36 if it happens when you bet it. But here's how casinos make money: the prize is less than $36, like maybe 34 or 33. So it's nice if you bet $1 and you win $33, but you're not going to win very often. And if you play the game in the long run, you'll be giving them $36 eventually in the long run one time that you get $33 back from them. And that's how casinos make money. They're in it for the long haul. They're happy to pay big jackpots to people because it makes people want to play more. Every time the game's played, on average, they're making a little bit of money. So they're slowly taking in small amounts of money that adds up over time, and then they can happily pay out big jackpots to get people to play more. Okay, another common game that young kids play are games with spinners. So I don't know, this may or may not be from a game, but here's a spinner right here. It's got 3 red, 2 green, and 1 yellow section. So there's 6 total sections of the pie. And in theory, they're all equal in size. Otherwise, it's not a fair game. So we got 6 equal sections of the pie. That's out of 6 then. I know the total's 6. I always go after the total right away. So the top has to be 0 through 6. They could say, what's the probability the spinner lands on a blue section? Well, there are no blue sections. So it would be 0 out of 6 or 0. They want to know what's the probability it lands on a red section. Well, there's 3 equal red sections, so 3 out of 6. I have 3 good cases and 6 total. 3 out of 6 is 1 out of 2. Here's one with, I'm going to start at the top, the brown. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 equal sections. So the denominator is going to start off as a 10 unless it reduces. Find the probability the pointer lands in a brown region. Okay, some of them are brown. There are 1, 2, 3 brown sections. This one's kind of obscured a little bit. It's brown. So 3 out of 10. 3 out of 10 does not reduce. So that's it. Okay, so spinners, they're pretty easy to do. Another common thing in probability are what I call chart problems, where they have a category on the side of the chart, like here they have gender, male and female, and then they have ages on the other side of the chart. It's a two-way chart, and you got categories on the top and categories on the side. That's what I call a chart problem. So they can ask you to find the probability of anything on the side or anything on the top or both. So one thing that usually happens in these problems is that usually they make you add up the totals, especially if you're in a 1342 class. But here they were nice enough to do all the totals for me. So check if the totals are there or not. If they are, or if you have to do them yourself, this bottom right corner right here, this 30.3, that's the grand total. The bottom corner after the totals are done is the grand total. So this has to be something divided by 30.3 no matter what. Now here it says type an integer or a decimal, because since the problem's already in decimals, then this is a rare case where they're going to allow decimal answers. But even still, I'm going to write this first and then I'll figure out the decimal later. So I always put the total down. In the chart problem, the total is the bottom right corner, whether that's given to you or if you have to find it yourself. Now I'm going to check what are they asking me to find. Find the probability that a randomly selected person living alone in the region is male. So the only thing they're asking about is male out of all the categories I have. I have gender and I have ages. This one's only asking about gender. They want to know the probability of a male. It could have asked about somebody who's 35 to 44 years old. Or it could have asked somebody who's male and 35 to 44 years old. They could ask for both categories at the same time. But they're only asking for male. So find male in the chart, and then you go all the way across that row or column to the end where the totals are. This 12.2, that's how many good cases there are. 12.2 million or whatever this is. These are like people in a large state and just from census records. So 12.2 million out of the 30.3 million people in this region are males. That's your basic probability right there. That's where you do the good over the total. And you don't just look at the first, some people just look at the first male and they try to put 0.7 for the top of the fraction. But there's males that are 18 years old, some are 25, some are 35, 45, 65, 75. So it's anybody who's a male, all those different ages. Now, normally we would try to reduce a fraction. Luckily here we don't. This is easier when they let me do decimals. It's a little surprising that they haven't allowed this until this problem yet, but 12.2 divided by 30.3. So probability is often listed as a decimal. The one downside to decimals is this, that you get these big, long, messy decimals. But so it's not going to be an exact answer, but they say round to the nearest hundredth. The first decimal is called the tenth, and the second one is the hundredth. There is no oneth. So it goes tenths, hundredths, thousandths. If they want you to round to the hundredth, that's telling me 2 decimal places. So then I got to look at the third decimal. Is that 5 or higher? No. So then I'm going to leave this 0.40. 0.40 or 40% of the population is male in this region. But don't put a percent because it didn't ask for that. So 0.40. So here's another chart problem. This last one just asked for male. Now they're just asking for an age. But I'm looking at my grand total in the bottom right corner, 29.4. That's definitely going to be the denominator before I whip out a calculator. Now I check what they want me to find. Find the probability somebody living alone is in the 25 to 34 age range. So 25 to 34, that's up here at the top of the chart. Now the gender doesn't matter, and I'm going straight to the end of that column, 4.2. So the previous problem, it was only about going across the males. We didn't care about the ages. Now we're going down in age, and we don't care about the gender. 4.2 divided by 29.4. The grand total changed, but that's just because I'm doing another problem. If they would have made a part A, a part B, and a part C, then I could have had the same grand total all 3 times. But now I got 0.14 again, and there's still a 2. Last time there was a 0 here, now there's a 2 here, but that's still not big enough to... Oh no, I guess it's different. I had 0.40 before. But 142, the 2's not big enough to add 1 to the 4, so leave that 0.14. I thought by coincidence I had the same answer, but it was 0.40, the previous problem. And then I think the final problem, 15, is going to be where you do both at the same time, like a male and somebody who's 25 to 34 years old. So I got another chart problem. Now the grand total is 29.5. So that's in the denominator before I calculate it. So now they want, find the probability that a randomly selected person in the region is a woman in the 18 to 24 age range. So they want both this time, a woman and to be 18 to 24 years old. So find woman in the chart, but don't go all the way to the end. Find the 18 to 24 up here, and where do these two meet each other in the table? 18 to 24 and woman, they meet right there where that 0.6 is. So then you just look at that one box only. Those are the 3 ways they can do these chart problems. They can just go all the way across a gender, go all the way down an age, or go to where they both meet each other. Those are the 3 kinds of questions they can ask. So 0.6 divided by 29.5. They did change the grand total all 3 times, but that's not hard because they do it for you anyway. When we do these in 1342, every time we get a new problem, we have to redo all the totals ourselves because they rarely give you the totals there. So this one is 0.020 So I don't need to add one. I'm just going to leave it 0.02. It's only a 2% chance of that, 0.02. Okay, so again, notice we had 15 problems in section 11.3 and another 15 in section 11.4, and I still finished in just over an hour. These problems go quicker at least. That's one nice thing here. The calculations aren't too difficult. Probably the hardest thing is reducing fractions, which a lot of people don't like. So both 11.3 and 11.4 are completed now. So this is our 4th week of the semester. And this is for Monday, August 7th. And then this is the 4th week. All the stuff's due Saturday, August 12th. So we just did 11.3 and 11.4 here for the Monday, August 7th. Tuesday, August 8th, we do 11.5 and 11.6. Wednesday, August 9th is 12.1 and 12.2. And then Thursday, August 10th is the last day of learning new material, 12.3 and 12.4. So this final week, we've got 4 sections of Chapter 11 and 4 sections of Chapter 12. And then you'll be taking the last regular test just over these 8 sections by Saturday, August 12th. And then next week, the only thing we do is review for the final. So we'll have the 4 days. There'll be 4 videos next week that will cover each of the 4 reviews. Even if you've done them already to help get ready for the other tests, it doesn't hurt to do them again when you're getting ready for the final. And I made those in having the final in mind, but they're also good to look at while you're studying for your test too, if you have the time. Okay, so that's it for Monday, August 7th. We did 11.3 and 11.4 today.